Subscribe to the channel and like the video. How did atoms come from nothing? It's one of those profound questions that reaches deep into both science and philosophy. When we look around at the universe, at the stars scattered across the night sky, at the planets, the oceans, the trees, and even ourselves, everything we see, touch, and experience is built from atoms. These tiny building blocks make up the foundation of reality. But here's the mind-bending part: atoms didn't always exist. There was once a time when there were no atoms, no stars, no planets, not even space or time as we understand them. So the real question is, how did something as fundamental as atoms arise from what seems like nothing? This is not just a scientific inquiry, it's a question that tugs at our very sense of existence. If we can understand where atoms came from, we are really asking how the universe itself came to be. This question invites us to step outside of ordinary thinking, to push beyond the everyday, and to peer into the origins of everything. Why does it matter where atoms come from? At first glance, it may seem like a distant, almost academic curiosity. After all, atoms are invisible to the naked eye. They're too small for us to see without sophisticated instruments, and they've been around for billions of years before humans ever walked the earth. But if you pause and really think about it, the importance of understanding the origin of atoms reaches into everything that makes up who we are and what we experience. It's not just about physics or cosmology, it's about life itself, about meaning, about where we fit into the story of the universe. When we ask how atoms came to be, we're not just asking a scientific puzzle. We are uncovering the grand narrative of existence, one that ties together galaxies, stars, planets, life forms, and ultimately the consciousness that wonders about its own origins. Every single thing you've ever touched, every breath you've ever taken, every thought you've ever had, all of it is made possible because of atoms. The oxygen you inhale is a collection of atoms. The water that keeps you alive is hydrogen and oxygen bound together. The calcium that gives your bones their strength is arranged in intricate atomic lattices. Even the electrical signals in your brain that allow you to listen, to think, and to dream are made possible by atoms, by the movement of ions, by the interaction of molecules, by the chemistry of carbon and nitrogen and phosphorus. Atoms are not just abstract entities hidden away in textbooks, they are the very scaffolding of your being. So when we ask where atoms come from, we are, in a very real sense, asking where we come from. Understanding their origin connects us directly to the birth of the universe. It reveals that our existence isn't separate from the cosmos, it is a continuation of it. The iron in your blood was forged in the heart of a star that exploded billions of years ago. The carbon that forms the backbone of every biological molecule in your body was once part of a stellar furnace. The atoms that allow you to sit here, to listen to this story, were once drifting in interstellar space, waiting for gravity to pull them together into new structures. This is why it matters, because it tells us that we are not isolated observers standing apart from the universe, but rather, we are expressions of it. The story of atoms is the story of us. If atoms had never formed, there would be no stars, no galaxies, no planets, and no life. Without atoms, there is only an empty energy field with no structure, no complexity, and no possibility of consciousness. The emergence of atoms is the critical turning point that made everything else possible. Beyond the personal connection, understanding the origin of atoms also allows us to grasp the scale and beauty of the universe. It gives us a map of cosmic history. Scientists can look at the oldest light in the universe, the cosmic microwave background, and see the fingerprints of the moment atoms first came into existence. That discovery doesn't just confirm theories, it shows us how deeply the birth of atoms is woven into the fabric of cosmic time. The very fact that we can look out across billions of light years and see evidence of this process is a reminder that atoms are universal. The same laws that formed hydrogen in the early universe also formed the hydrogen in your body. The same physics that created helium billions of years ago still governs the helium atoms floating in the sun today. And when we understand atoms, we also gain insight into the evolution of complexity. The universe didn't start with life. It didn't start with galaxies or planets. It began with the most basic ingredients, and from those ingredients, over vast spans of time, complexity emerged. Atoms allowed molecules to form. Molecules allowed chemistry to happen. Chemistry allowed biology to spark. And biology eventually gave rise to beings who could ask the question we are exploring right now. By studying the origin of atoms, we can trace the ladder of complexity back to its first rung, and appreciate how fragile and precious our existence really is. There's another reason why it matters, and it's more philosophical. Human beings are wired to seek meaning. We want to know not only how things work, but also why they are the way they are. When we investigate the origins of atoms, we satisfy that deep need for connection and understanding. We discover that the universe is not random chaos, but a place where order emerges, where patterns form, where matter organizes itself into stars and life and consciousness. This knowledge can be humbling, because it reminds us that we are tiny compared to the scale of the cosmos. But it is also empowering, because it reveals that we are, in fact, the universe aware of itself. Think about it this way. Billions of years ago, in the aftermath of the Big Bang, energy condensed into particles. Those particles formed atoms. Those atoms gathered into stars. Those stars forged heavier elements. Those elements became the building blocks of planets and living organisms. And now, here you are, listening to these words, contemplating the very process that made you possible. That cycle of transformation, from the simplicity of energy to the complexity of a thinking mind, is one of the greatest stories ever told. And it all hinges on atoms. Finally, understanding where atoms come from matters because it pushes the boundaries of science itself. It forces us to confront the deepest mysteries. What is nothing? Why is there something rather than nothing? What laws of physics allowed atoms to arise? By asking these questions, we don't just learn about atoms. We challenge ourselves to explore the edges of knowledge, to probe the unknown, and to expand the horizons of human understanding. The origin of atoms is not a closed chapter. It's a doorway into even greater mysteries about dark matter, dark energy, and the ultimate fate of the universe. So yes, this question matters. It matters scientifically, because it explains the structure of the universe. It matters personally, because it explains the structure of us. It matters philosophically, because it ties us into a greater cosmic narrative. Without atoms, there is no story. With them, there is everything: stars, galaxies, planets, life, and consciousness. Understanding where they came from helps us grasp not only the mechanics of reality, but also the wonder of our place within it. When we ask how atoms could have come from nothing, we have to pause and carefully examine what we mean by that word. Because in everyday language, nothing usually means a total absence, a complete void, a place where absolutely nothing exists, not even space or time. But in physics, the word nothing carries a very different, and much more intriguing, meaning. If we're going to understand how the universe could have begun, and how atoms could eventually emerge, we need to clarify what scientists actually mean when they talk about nothingness. In common thought, nothing is emptiness, like an empty room with no furniture, no air, no light. But even that isn't true nothingness, because the room itself still exists. There are still walls, space, and time. True nothing, in the strictest philosophical sense, would mean no space, no time, no energy, no laws, no possibility of anything at all. But physics doesn't really deal with that kind of absolute void. Instead, when physicists talk about nothing, they often mean the quantum vacuum. And here's the mind-bending part: a quantum vacuum isn't empty. It isn't barren. It is a sea of possibilities, a restless, fluctuating backdrop that never truly sits still. In quantum mechanics, the idea of emptiness is transformed. Even in the vacuum of space, where you might think there is nothing at all, there are still fields. These fields are invisible scaffolding that permeate reality. Quantum field theory tells us that what we perceive as particles are really excitations, or ripples, in these underlying fields. So even when no particles are present, the fields themselves remain, and they never fully quiet down. At the smallest scales, they are alive with fluctuations, little blips of energy appearing and disappearing spontaneously. These fluctuations mean that what we call nothing is actually buzzing with activity. Virtual particles, temporary pairs of matter and antimatter, can pop into existence and vanish again almost instantly. They don't last long enough to be observed directly, but their effects can be measured. In fact, experiments like the Casimir effect show us that even empty space has energy, because the behavior of plates placed very close together reveals the influence of these vacuum fluctuations. So in the language of physics, nothing is not a void but a dynamic, energetic stage on which the drama of existence can begin. This reshaping of nothing also changes how we think about the origin of atoms. If we imagine that the universe began from an absolute void, with literally no potential for existence, then the question of atoms arising from nothing seems impossible. But if we think of nothing in the scientific sense, as a quantum vacuum filled with fields and fluctuations, then the question becomes more approachable. Perhaps the seeds of existence were always embedded in the very nature of reality itself. Perhaps the quantum vacuum is the canvas, and the Big Bang was the moment when its latent energy burst forth into the structure of space and time. It's also important to realize that in quantum physics, energy conservation doesn't work exactly the same way at the smallest scales. On extremely tiny timescales, energy can appear and disappear, as long as it balances out overall. That's why virtual particles can pop into existence momentarily. This principle suggests that a universe could, in theory, emerge from a state of nothing, because what we think of as nothing is actually a restless quantum froth that allows fluctuations to occur. Those fluctuations might have been enough to spark the expansion we call the Big Bang, eventually giving rise to atoms and everything else. Of course, there's still a philosophical tension here. If we call the quantum vacuum nothing, some would argue that it isn't really nothing at all, because it still has laws, structure, and potential. The fact that it allows fluctuations means it isn't truly void. And that's true. Scientists themselves debate what nothing really means. But what's clear is that physics has redefined the concept away from emptiness and toward possibility. The nothing that preceded atoms was not sterile, it was fertile, full of the ingredients for creation. This redefinition is not just a semantic trick. It's a crucial shift in perspective that allows us to trace a logical path from the apparent emptiness of the early universe to the complexity of atoms and galaxies. Without understanding what nothing really means in physics, the leap from non-existence to existence seems magical or impossible. But when we realize that nothing is actually a quantum vacuum, governed by laws and rich with energy, then the leap becomes a natural consequence of those laws. The universe becomes not a miracle from nowhere, but an unfolding from the fabric of reality itself. So when we ask how atoms came from nothing, we are not talking about atoms appearing from a pure void with no rules or possibilities. We are talking about atoms emerging from a quantum field, from a vacuum that seethes with fluctuations, from a foundation that, while invisible, is anything but empty. This subtle but profound distinction sets the stage for the story of the universe's birth, because it tells us that even in nothingness, the seeds of everything were already present. To truly understand how atoms came from nothing, we need to set the stage with a timeline, because the birth of atoms wasn't an instant event, it was a gradual unfolding, stretched across hundreds of thousands of years, and influenced by conditions so extreme that it challenges our imagination. The story of atoms is really the story of the universe itself, unfolding in key stages, each building on the last, leading eventually to the moment when the first true atoms could finally exist. By mapping out this timeline, we see that the universe went through a kind of childhood, messy, chaotic, and fiery, before it matured enough to give birth to the basic building blocks of matter. The timeline begins about 13.8 billion years ago with the event we call the Big Bang. And it's important to emphasize from the start that the Big Bang was not an explosion in space, as we often picture it. It was the rapid expansion of space itself, carrying energy outward in all directions. At the moment of this beginning, there were no atoms, no stars, no galaxies, only energy compressed into an almost incomprehensibly hot and dense state. This is time zero, the moment everything began. From that moment, the universe expanded and cooled, and in just a fraction of a second, less than 1/trillionth of a second, an era called cosmic inflation occurred. During inflation, the universe ballooned exponentially in size, smoothing out irregularities and setting the conditions for everything to follow. Even though inflation lasted for only a tiny sliver of time, it had permanent effects. It seeded the small variations that would eventually form galaxies, stars, and planets. Within the first second after the Big Bang, the universe was still unimaginably hot, with temperatures reaching over 10 trillion degrees. At this stage, the only things that existed were fundamental particles and radiation. Energy dominated, but thanks to Einstein's famous equation E equals mc squared, some of that energy began transforming into matter. Particles like quarks and electrons came into being, although they were still far too energetic to bind into anything stable. It was a swirling soup, a plasma of particles and light, colliding and annihilating each other in a storm of creation and destruction. By about 1 microsecond after the Big Bang, the temperature dropped enough that quarks could bind together, forming the first protons and neutrons. This was a critical step forward. Instead of fleeting particles flashing in and out of existence, the universe now had stable building blocks, ingredients that could later assemble into nuclei. But at this point, there were still no atoms. Everything existed as free protons, neutrons, electrons, and radiation, locked in a hot, dense plasma. Fast forward to about 3 minutes after the Big Bang, and we reach a stage called Big Bang nucleosynthesis. Here, the universe had cooled enough for protons and neutrons to fuse into light nuclei. During this brief window of a few minutes, the first atomic nuclei were created: hydrogen nuclei, which are just protons, helium nuclei, and tiny traces of lithium. But again, we must stress, these were nuclei, not atoms. Electrons were still flying freely, unable to settle into stable orbits because the universe was still far too hot and energetic. For the next 380,000 years, the universe remained in this plasma state, a fog of nuclei, electrons, and photons constantly colliding. Photons, the particles of light, couldn't travel far before bouncing off free electrons, which meant the universe was opaque, like a glowing soup. If you were able to look into the cosmos during this time, you wouldn't see stars or galaxies. It would be like staring into a brilliant, blinding fog. Finally, after 380,000 years, the universe cooled enough for electrons to slow down and combine with nuclei. This event, known as recombination, marked the birth of true atoms. Hydrogen atoms formed in vast numbers, along with helium atoms and a smattering of lithium. With electrons finally bound to nuclei, photons could travel freely through space, and the universe became transparent for the first time. The light released at that moment is what we now detect as the cosmic microwave background, a faint afterglow of the early universe. That moment, 380,000 years after the Big Bang, was the turning point when atoms truly came into existence. For the first time, the universe had stable, neutral matter that could interact in new ways. These simple atoms of hydrogen and helium were the raw materials from which everything else would eventually form: stars, galaxies, planets, and life. So, the timeline from nothing to atoms looks like this: the Big Bang at time 0, cosmic inflation in the first split second, the formation of quarks, protons, and neutrons within microseconds, the fusion of nuclei within minutes, hundreds of thousands of years of hot plasma, and finally, the recombination event when electrons joined nuclei to form the first atoms. This grand sequence sets the foundation for the rest of cosmic history, because once atoms existed, they could clump together under gravity, fueling the birth of stars and galaxies. When we lay it out this way, it becomes clear that atoms didn't just appear suddenly. They were the outcome of a long chain of events, each governed by the laws of physics, each stage dependent on the cooling of the universe as it expanded. From nothing, energy arose. From energy, particles emerged. From particles, nuclei formed. And from nuclei, after nearly 400,000 years, atoms finally took shape. That's the astonishing timeline of how the building blocks of matter were born. When people hear the words Big Bang, the image that often comes to mind is that of a giant cosmic explosion, like a massive bomb going off in some pre-existing emptiness, scattering pieces of matter outward into space. But this picture, while vivid, is misleading. The Big Bang wasn't an explosion of matter into empty space. It was the expansion of space itself, carrying energy and matter with it. To really appreciate how atoms came from nothing, we need to peel back the popular misconceptions and see what the Big Bang actually was. At the very beginning, about 13.8 billion years ago, everything that would ever exist, the galaxies, stars, planets, even the atoms in your body, was compressed into a state of unimaginable density and temperature. It wasn't sitting in a vast empty void. There was no outside for it to explode into. Space itself didn't exist yet. Time itself hadn't begun. The Big Bang marks the birth of space and time as we know them. Instead of thinking of it as an explosion, imagine it as space stretching and expanding, with every point moving away from every other point. There was no central spot where it began. Everywhere was the center, because space itself was being created in the process. This is one of the most difficult ideas for our human minds to grasp, because we are so used to explosions happening within a space, like fireworks in the night sky. But the Big Bang was fundamentally different. It wasn't something happening in the universe, it was the universe itself coming into being and immediately beginning to expand. Every bit of matter and energy was compressed into an incredibly tiny region, and then the fabric of space began to stretch, carrying everything outward. In those earliest instants, conditions were extreme beyond anything we can recreate today. Temperatures soared to trillions of degrees. Densities were so high that ordinary matter as we know it couldn't exist. Instead, there was a roiling soup of pure energy and fundamental particles flashing in and out of existence. The universe was smooth and uniform at large scales, but filled with tiny quantum fluctuations, minute differences in density, that would eventually grow into galaxies, stars, and planets. The Big Bang was also not loud, because sound requires air or some kind of medium to travel through, and none of that existed then. Instead, it was silent, and yet unimaginably powerful. It was the moment the universe leapt into being, expanding not into something, but expanding itself. This expansion continues even now. The galaxies we see in the night sky are all moving away from us, not because they are flying through space like shrapnel from an explosion, but because the fabric of space itself is stretching, carrying them farther apart. Another key misconception is that the Big Bang was a single event that happened and then ended. In reality, the Big Bang describes an ongoing process. The expansion it set into motion has never stopped. From that initial moment, the universe has been expanding, cooling, and evolving for billions of years. In fact, scientists have measured this expansion today by observing the redshift of light from distant galaxies. The farther away a galaxy is, the faster it appears to be receding, which is exactly what we would expect if space itself is stretching. So when we say Big Bang, what we really mean is the rapid expansion of space and the transformation of energy into the building blocks of matter. There was no center, no edge, and no outside. Every part of the universe was once compressed together, and every part has been moving apart ever since. This distinction matters because it changes how we think about the origins of atoms. If we imagine the Big Bang as an explosion, then atoms might seem like debris blasted outward into empty void. But if we recognize the Big Bang as an expansion of space and energy, we see atoms not as fragments of an explosion but as structures that emerged naturally as the universe cooled. The Big Bang wasn't the scattering of pieces, it was the unfolding of potential. It was the process that turned nothing into everything, setting the stage for quarks, protons, neutrons, and eventually atoms to form. And while the Big Bang is often framed as a singular point in time, scientists sometimes describe it more precisely as the beginning of the observable universe. What happened before it, or whether the question of before even makes sense when time itself began there, is still an open mystery. But what we do know, with remarkable confidence, is that the Big Bang describes the expansion that brought space, time, energy, and the laws of physics into being. That expansion created the conditions under which, hundreds of thousands of years later, atoms could finally exist. So the Big Bang was not an explosion in the emptiness of space. It was space itself bursting forth, expanding with energy, filled with potential. And within that expansion, the universe began its long journey from chaos to structure, from energy to matter, from nothing to atoms. At the very beginning of the universe, before atoms existed, before protons or neutrons had even formed, there was only energy. This is one of the most astonishing and counterintuitive aspects of the universe's story. Everything we see today, from galaxies and stars to mountains and oceans to the atoms in your own body, all trace back to an initial state of pure energy. The universe didn't begin with matter. It began with energy, raw and undifferentiated, contained within an unimaginably hot and dense environment. When the Big Bang occurred, the temperatures were so extreme that matter, as we understand it, couldn't possibly exist. The conditions were simply too violent. The fabric of the universe was flooded with radiation, seething at energy levels trillions of times greater than anything we could ever achieve on Earth. It's difficult to even picture this moment because everything we know about the physical world, atoms, molecules, structures, didn't apply yet. What existed was a kind of primordial fire, a sea of energy where particles flickered in and out of existence too quickly to become anything stable. This concept of only energy may sound abstract, but Einstein gave us the key to understanding it with his famous equation, E equals mc squared. What this tells us is that energy and matter are interchangeable. They are two expressions of the same fundamental reality. Matter is essentially frozen energy, bound into stable forms. But at the very start, the universe was so hot that no energy could settle into matter. It remained as radiation, pure and unformed, waiting for the universe to cool down enough for particles to emerge. In those first instants, there were fluctuations, tiny, quantum ripples in this sea of energy. These ripples may seem insignificant, but they were crucial. Over billions of years, they grew into the massive structures we see in the cosmos today: galaxies, clusters of stars, and planetary systems. In other words, even at the stage when there was only energy, the seeds of everything to come were already present in the form of minuscule variations. The dominance of energy at the beginning also explains why the universe expanded so quickly. Energy has pressure, and in such an extreme concentration, that pressure was colossal. It drove space itself to stretch at an incredible rate. This rapid expansion, combined with cooling, gradually created the right conditions for matter to appear. Without this initial period of pure energy, there would never have been a transition to particles, nuclei, atoms, and eventually, stars and life. It's also worth noting that we still live in a universe where energy plays the central role. Even now, much of the cosmos is filled with radiation, dark energy, and other forms of energy we barely understand. Matter, the atoms that make up you, me, the planets, and the stars, is actually just a tiny fraction of the universe's total composition. The early state of pure energy reminds us that matter is not the default condition of reality. Instead, matter is a later development, a consequence of cooling and transformation. At the dawn of time, then, there were no atoms to speak of, only raw energy permeating a newborn universe. This was the blank canvas, the stage before particles, before chemistry, before physics as we normally experience it could take hold. Only as the universe expanded and cooled did this energy begin to crystallize into matter. The transformation of energy into particles, and eventually into atoms, is the great alchemy at the heart of the universe's origin story. Without the initial ocean of energy, there could be no quarks, no protons, no neutrons, and ultimately, no atoms. So the first chapter of the universe was not one of matter, but of energy alone, blinding, powerful, and chaotic. And from this foundation of pure energy, everything else was destined to unfold. Einstein's equation, E equals mc squared, is perhaps the most famous scientific formula ever written, and it holds the key to understanding how a universe, which began as pure energy, could eventually give birth to matter, and therefore atoms. At first glance, the equation seems deceptively simple. Energy, E, equals mass, m, multiplied by the speed of light, c, squared. But hidden within this elegant relationship is one of the most profound truths in physics, that energy and matter are interchangeable. They are not separate categories of reality, but two faces of the same coin. To see why this is so revolutionary, consider what the equation tells us. Mass, which we think of as the stuff that makes up objects, the matter you can hold, touch, or stand on, is not a permanent, independent quantity. It is, in essence, just a concentrated form of energy. The c-squared part, the speed of light squared, acts as a conversion factor. Because the speed of light is so staggeringly large, squaring it produces an enormous number. That means that even a tiny amount of mass contains an immense amount of energy. This is why nuclear reactions, which convert just small amounts of matter into energy, release such colossal power. But if matter can be turned into energy, as we see in nuclear explosions or in the burning core of the sun, then the reverse must also be true. Energy can be transformed into matter. And this is precisely what happened in the early universe. In the fiery, energetic conditions right after the Big Bang, energy was constantly colliding and transforming into particles of matter and their counterparts, antimatter. Particles would appear, annihilate, and reappear in a constant dance. The hot, dense environment made these transformations possible. What makes Einstein's equation so critical here is that it shows us how matter didn't need to exist from the start. It could emerge from pure energy. The protons, neutrons, and electrons that would later form atoms weren't sitting around waiting. They were created as the universe cooled, each one a frozen packet of energy stabilized into mass. This is the bridge between the era of energy and the era of matter. Without E equals mc squared, there would be no logical pathway to explain how the universe transitioned from an initial state of pure radiation to a universe filled with tangible, structured matter. The implications go beyond cosmology. E equals mc squared tells us that the boundary between what we call matter and what we call energy is not fixed but fluid. Stars, for example, rely on this very principle. In their cores, hydrogen atoms fuse into helium, and a fraction of their mass is converted into energy. That energy then radiates outward as light and heat, sustaining life on planets like Earth. At the same time, in high-energy collisions within those stars, some of that energy is transformed into heavier elements. The universe has been conducting this transformation for billions of years, turning energy into matter, and matter back into energy, in an endless cycle governed by Einstein's insight. For the early universe, however, this process was especially crucial. The sheer intensity of energy present immediately after the Big Bang was sufficient to create the first stable particles. Without E equals mc squared, those particles, and eventually atoms, would never have existed. It's remarkable to realize that the equation Einstein wrote down in 1905 is not just an abstract idea on paper. It describes the very engine that powered the creation of everything around us. And it's not only about creation, it's about possibility. Because energy and mass are equivalent, the universe had the flexibility to evolve. It wasn't locked into being a chaotic sea of radiation forever. Energy could condense into particles, those particles could combine into nuclei, and much later, atoms could form. From that point onward, chemistry, biology, and eventually conscious life could emerge. All of it flows from the fundamental truth encoded in E equals mc squared. So when we say that the universe began with energy and somehow produced matter, it isn't magic or mystery, it's physics. Einstein showed us the rulebook. Energy can transform into mass, and mass into energy, seamlessly and naturally. Atoms exist because energy had the capacity to change its form, to condense into the matter that would one day shape stars, galaxies, and human beings. This is why E equals mc squared is not just a scientific equation, but one of the most profound bridges between the abstract mathematics of physics and the tangible reality of existence. As the universe continued its expansion after the Big Bang, something extraordinary began to happen. The seething ocean of pure energy that once dominated everything started to cool, and as it cooled, it made possible the birth of the very first particles. This is where the transformation from pure energy into matter truly began, a process that would eventually lead to the creation of atoms. But before atoms could form, the universe first needed its most basic building blocks, fundamental particles such as quarks and electrons. In those earliest fractions of a second, the universe was unimaginably hot, so hot that no particle could exist for more than an instant. Any time a particle managed to appear, it would almost immediately collide with its opposite, like a particle meeting its antiparticle, and annihilate back into energy. The environment was a storm of creation and destruction, with particles flickering into existence and vanishing just as quickly. It was chaos, a kind of quantum dance where nothing could settle down long enough to become stable. But as the universe expanded, it cooled. And cooling was the crucial step. Think of it like steam condensing into water as it loses heat. At extremely high temperatures, steam is free and chaotic, but as it cools, it organizes into droplets of liquid. The early universe followed a similar principle. As the searing energy levels dropped, it allowed particles to condense out of the energetic soup and become stable. Energy transformed into matter, and the first quarks and electrons began to persist instead of instantly annihilating. Quarks were among the earliest of these fundamental particles to take hold. Quarks are incredibly tiny, indivisible units that come in different flavors, such as up quarks and down quarks. These might sound like playful names, but they represent the fundamental differences in the way quarks behave and interact. At this stage in cosmic history, the universe was filled with a vast population of quarks, moving freely in a dense plasma along with their antimatter counterparts, antiquarks. Electrons also emerged during this cooling period. Unlike quarks, electrons do not combine with one another to make larger particles. Instead, they would later serve as the orbiting partners of atomic nuclei, giving structure and stability to atoms. In these earliest moments, however, electrons were still free-floating, like restless dancers without partners, drifting through the hot plasma, unable yet to settle into stable orbits. The key here is that all of these particles, quarks and electrons, are not creations pulled from outside the universe. They are the natural expressions of energy when conditions allow. Energy itself, when cooled, reveals matter. It's as if the universe had hidden instructions encoded within its laws, ensuring that once the right temperature was reached, energy would inevitably crystallize into particles. Without this phase transition from energy to quarks and electrons, the universe could never have taken the next step toward atoms, chemistry, and life. Another important thing to understand is that not every particle survived. For every billion particles of matter that came into existence, there was almost an equal number of antiparticles. When they collided, they annihilated one another, turning back into energy. But somehow, in a great cosmic asymmetry that scientists still don't fully understand, there was a slight excess of matter over antimatter. That tiny imbalance, just one extra particle of matter for every billion annihilations, was enough to leave behind the matter that makes up everything we see today. If not for this imbalance, the universe would have returned to pure energy, and atoms would never have formed. By the time the universe was just microseconds old, quarks had stabilized enough to dominate the landscape, along with electrons and other lightweight particles. The stage was now set for the next great transformation, the binding of quarks together to form protons and neutrons. But at this point in the story, it's crucial to recognize the profound shift that had already taken place. From the raw furnace of pure energy, through the cooling of the cosmos, the universe had given birth to its first constituents of matter. So, particle formation marks the first true bridge between nothingness and the tangible reality we recognize. Energy condensed into quarks, the seeds of protons and neutrons, and electrons, the companions that would one day orbit atomic nuclei. These weren't atoms yet, far from it. But they were the essential ingredients, the letters of the cosmic alphabet, waiting to be assembled into the words, sentences, and stories of the universe. Once the universe cooled enough for quarks to persist, the next step in the journey toward atoms was their binding together into larger, more stable structures. This was the dawn of protons and neutrons, and at the heart of this process was one of the strongest and most fascinating forces in nature, the strong nuclear force, carried by particles known as gluons. To understand how the first atomic building blocks came into existence, we need to look closely at the strange and beautiful relationship between quarks and gluons. Quarks, as we've seen, are fundamental particles. They are among the smallest constituents of matter, indivisible and elementary. They come in 6 different flavors: up, down, charm, strange, top, and bottom. But in the early universe, the most important ones were the up quarks and down quarks. These would become the foundation of the first protons and neutrons. However, quarks cannot exist in isolation. Unlike electrons, which can move freely through space, quarks are always bound together. And the reason for this lies in the nature of the strong force. The strong nuclear force is, as its name suggests, extraordinarily powerful. Much stronger than gravity, stronger than electromagnetism, and even stronger than the weak nuclear force that governs radioactive decay. It is the glue that holds the nucleus of an atom together, and at the most fundamental level, it is mediated by gluons. Gluons are force-carrying particles, similar in principle to how photons carry the electromagnetic force. But gluons are unique because they not only bind quarks together, they also interact with each other, weaving an inseparable web of connection that locks quarks tightly into groups. In the early universe, about a millionth of a second after the Big Bang, quarks found themselves drawn into these groups by gluons. 3 quarks at a time were pulled together to form what we call baryons. The most important baryons in our story are the proton, made of 2 up quarks and 1 down quark, and the neutron, made of 1 up quark and 2 down quarks. These particles are the stable building blocks of atomic nuclei, and their formation was a pivotal turning point in cosmic history. It's worth pausing to marvel at how strange and non-intuitive this is. Quarks, governed by the strong force, behave differently from anything in our macroscopic world. For example, if you try to pull quarks apart, the force between them doesn't weaken like gravity or magnetism. It actually grows stronger the farther apart they get. This means quarks are permanently confined. They cannot escape the bond of gluons. If you try to separate them, Eventually enough energy is pumped into the system that new quark-antiquark pairs simply pop into existence, ensuring quarks are never found alone. This phenomenon, known as confinement, is why we never see a lone quark floating in space. They are always bound, always tied together in larger structures. This confinement is also what allowed the universe to make the leap from a chaotic quark-gluon plasma to stable protons and neutrons. As the temperature fell, the strong force locked quarks into these trios, forming the first stable hadrons. And once protons and neutrons existed, the foundation was laid for the next step, the fusion of these particles into simple atomic nuclei. One of the fascinating consequences of this process is that it highlights just how finely tuned the laws of physics are. If the strong force had been slightly weaker, quarks might never have bound together, leaving the universe as a soup of particles with no stable matter. If it had been slightly stronger, matter could have collapsed into unworkable configurations, preventing the kind of chemistry that makes life possible. But as it is, the strength of the strong nuclear force is just right to bind quarks into protons and neutrons, stable enough to persist for billions of years. At this stage in the universe's development, there were still no atoms. But the basic nuclei, the heart of what would become atoms, were beginning to take shape. Protons, positively charged, and neutrons, electrically neutral, were now abundant. Alongside them, electrons still roamed free, waiting for their chance to one day orbit these nuclei. The universe had gone from a soup of fundamental particles to the first composite structures, thanks entirely to the tireless work of gluons stitching quarks together. So the story of quarks and gluons is the story of how chaos began to give way to order. From the wild plasma of the newborn cosmos, quarks, held together by the strongest force in nature, became the protons and neutrons that would form the heart of every atom in existence. Without gluons, without the strong nuclear force, there would be no stable matter, no atoms, no stars, no life. Every breath you take is possible because billions of years ago, quarks bound together into the first protons and neutrons, laying the foundation for everything to come. With quarks bound into protons and neutrons by the strong force, the universe had taken a monumental step forward. But it was still far from forming the atoms we know today. The next chapter in this unfolding story came just minutes after the Big Bang, in an event known as Big Bang nucleosynthesis, the cosmic forging of the very first atomic nuclei. This was a brief but profoundly important era in which the first simple elements, hydrogen, helium, and a trace of lithium, were born. The key to this process was temperature. In the earliest instance, the universe had been so incredibly hot that any attempt by protons and neutrons to fuse would have been immediately undone by the sheer violence of the environment. Imagine trying to glue pieces of paper together in the middle of a roaring fire. Before the glue can set, the heat tears everything apart. That's what the universe was like in those first seconds. But as expansion continued, the temperature dropped. By the time the universe was about 3 minutes old, it had cooled to around 1 billion degrees Kelvin, a temperature still unimaginable by earthly standards, but just right for nuclear fusion to take place. At this moment, protons and neutrons were abundant, floating freely in the hot plasma. The strong nuclear force, which had already bound quarks into protons and neutrons, now went to work again, this time binding those protons and neutrons together into larger structures, the first nuclei. The simplest nucleus was hydrogen, which is just a single proton on its own. But when protons and neutrons fused, they formed deuterium, 1 proton and 1 neutron, and then helium, 2 protons and 2 neutrons. A small amount of lithium also emerged, though in tiny traces compared to hydrogen and helium. This fusion process didn't last long. In fact, Big Bang nucleosynthesis only lasted for a matter of minutes, because as the universe continued to expand, it cooled further, and the energy levels dropped below what was required for nuclear reactions to keep happening. Once that window closed, the universe essentially froze in the ratio of elements it had produced. And here's the fascinating part. The universe ended up being overwhelmingly dominated by hydrogen, with about 25% of its mass in helium, and just trace amounts of lithium. These simple nuclei became the raw material for all future chemistry. It's worth emphasizing how critical this brief era was. Without it, the universe would have been a sea of protons and neutrons that never fused into anything larger. There would be no helium, no lithium, and later on, no foundation for stars to perform their cosmic alchemy of forging heavier elements. Hydrogen and helium nuclei were like the scaffolding of the universe's future, the base layer upon which everything else would eventually be built. At this stage, however, there were still no atoms. The nuclei existed, but the universe was still far too hot for electrons to attach themselves to these nuclei and form neutral atoms. Instead, the environment remained a glowing plasma, where light and matter were constantly colliding. Electrons continued to fly freely, bouncing off photons and preventing the formation of stable atoms. In other words, the universe had nuclei, but it didn't yet have the calm, structured atoms that would one day make molecules, stars, and planets possible. Nevertheless, the creation of these first nuclei was a monumental step. Think about it. In just the first few minutes of its life, the universe had already decided the broad chemical composition that would persist for billions of years. To this day, when we look out into the cosmos, we find that about 3/4 of all matter is hydrogen and most of the rest is helium, with heavier elements making up only a tiny fraction. This distribution was set in stone during Big Bang nucleosynthesis, and it is one of the most powerful confirmations of the Big Bang theory. When scientists measure the abundance of these light elements and find they match the predictions of nucleosynthesis, it tells us we are reading the true history of the universe. So, a few minutes after the Big Bang, the first nuclei of hydrogen, helium, and lithium had formed. The universe had gone from energy, to particles, to protons and neutrons, and now to the first elements. It was still a long road before atoms could exist, but the heart of each atom, the nucleus, was now in place. These simple nuclei were the seeds of everything to come, waiting for the day, hundreds of thousands of years later, when they could finally capture electrons and become full-fledged atoms. After the first nuclei of hydrogen, helium, and a little bit of lithium had come into existence during Big Bang nucleosynthesis, the universe entered a new phase, a state that can best be described as a vast, glowing ocean of hot plasma. To understand why this was such a unique stage in cosmic history, we need to first be clear about what plasma actually is. Plasma is often called the fourth state of matter, distinct from solids, liquids, and gases. In plasma, atoms don't really exist as whole, neutral units. Instead, you have positively charged nuclei flying around freely, with electrons moving separately, unbound. In other words, it's a chaotic soup of particles where matter and energy are still deeply intertwined. At this point, the universe was still blisteringly hot. So hot, in fact, that it prevented electrons from settling into orbit around the newly formed nuclei. Imagine trying to place a tiny marble into orbit around a central ball, but every time you try, someone shakes the entire system violently enough to knock the marble away. That's essentially what was happening on a cosmic scale. Electrons would be drawn toward nuclei by electromagnetic attraction, but before they could settle, the intense heat and constant bombardment of high-energy photons would kick them back out. The result was a plasma state where no true atoms could exist. This era lasted for hundreds of thousands of years. During this time, the universe was filled with a dense fog of charged particles, protons, neutrons locked inside nuclei, and free-floating electrons, mixed with a flood of photons, or particles of light. But here's the critical thing: photons couldn't travel far without constantly colliding with these charged particles. Every time light tried to move through the universe, it was scattered almost immediately. The cosmos was effectively opaque, like a thick glowing mist, with no transparency at all. If you had been able to exist back then, you wouldn't have seen stars or galaxies. In fact, you wouldn't have been able to see anything beyond a glowing haze surrounding you, because light simply couldn't travel freely. This plasma state is one of the reasons why we sometimes describe the early universe as being in its childhood. It hadn't yet cooled or calmed down enough to allow atoms to form, and without atoms, there could be no chemistry, no stable structures, no galaxies. It was a universe still waiting for its first real clarity. Scientists know about this plasma state not by direct observation with the naked eye, of course, but by studying the cosmic microwave background radiation. This faint glow, detectable with sensitive radio telescopes, is the afterglow of the hot plasma universe. It's the fossil light left over from the time when the universe finally transitioned out of this opaque state into a transparent one. But before that great transition, before recombination, which would occur about 380,000 years after the Big Bang, the plasma ruled. It's worth emphasizing how extreme this era was. The temperatures were on the order of thousands of degrees Kelvin, comparable to the surface of a star. Under such conditions, it was simply impossible for electrons to remain bound to nuclei. The constant collisions between particles were too energetic, breaking apart any would-be atoms as soon as they started to form. This was not a calm environment. It was violent, chaotic, and blindingly bright, a glowing plasma storm stretching across the entire universe. And yet, even within this chaos, the seeds of order were already in place. Nuclei of hydrogen and helium were floating freely, electrons were abundant, and light was everywhere. The universe was like a great cosmic nursery, not yet ready for atoms, but preparing for the day when conditions would finally allow matter to take on its familiar, stable form. That day would come, but not for hundreds of thousands of years. Until then, the cosmos remained a radiant plasma, an endless sea of particles where light could not escape, and where the story of atoms was still waiting to begin its next chapter. Roughly 380,000 years after the Big Bang, the universe underwent one of its most transformative moments, a period scientists call recombination. Despite the name, it wasn't really a recombination, because electrons and nuclei had never been fully combined in the first place. A more accurate term might be combination, but in scientific tradition, the older name stuck. This was the era when electrons, for the very first time, were able to attach themselves to nuclei, giving birth to the first true atoms in the cosmos. To understand why this moment was so pivotal, let's return briefly to what the universe looked like just before recombination. It was still filled with a hot plasma of free nuclei and electrons, bathed in a sea of high-energy photons. Every time an electron tried to orbit a nucleus, photons, essentially particles of light, would slam into them with enough energy to knock them loose again. This relentless disruption made it impossible for atoms to form. The result was a universe that was bright but opaque, like a thick fog glowing from within, because photons couldn't travel far without colliding with charged particles. But over hundreds of thousands of years, the universe expanded, and as it expanded, it cooled. Eventually, the temperature dropped to about 3000 Kelvin, still hotter than the surface of a red-hot stove, but cold enough that the destructive collisions between photons and electrons became less frequent. At this temperature, electrons finally had a chance to stay bound to nuclei. This was the birth of neutral atoms. The most common atom to form during this time was hydrogen, the simplest and most abundant element in the universe. Each hydrogen atom was nothing more than a single proton with an electron orbiting around it. Helium, which had been created earlier during nucleosynthesis, also captured electrons to form neutral helium atoms. A tiny trace of lithium did the same. For the first time, the cosmos had stable, electrically neutral matter. And this changed everything. The instant electrons bound to nuclei, photons were no longer constantly scattered by free charges. Instead, light was free to travel vast distances through space without being interrupted. The universe, for the first time, became transparent. This release of photons into open space is what we now detect as the cosmic microwave background radiation, the oldest light we can observe. Every time scientists tune into this faint afterglow with their telescopes, they are literally seeing the moment when the first atoms were born. The recombination era was not just a technical milestone, it was a dramatic transformation in the character of the universe. Before recombination, the cosmos was a glowing fog where no structures could be seen. After recombination, space cleared, and light could move freely, carrying with it an imprint of the conditions of the early universe. That imprint still exists today as subtle fluctuations in the cosmic microwave background, giving us a kind of baby picture of the universe when it was less than 500,000 years old. Think about how profound this is. The first atoms formed at that moment. Without this step, nothing we know, no stars, no planets, no living beings, could have ever emerged. Atoms are the scaffolding of reality, and recombination was their first appearance on the stage of cosmic history. For the first time, the universe wasn't just a soup of particles, it had structure at the smallest level of matter. Another beautiful way to think about this is that recombination gave the universe its first true identity. Before, it was just raw potential, nuclei and electrons wandering through an opaque haze. After recombination, those same particles took on permanent partnerships, forming entities that would persist across cosmic time. A hydrogen atom created back then could, in principle, still exist today, unchanged for over 13 billion years. So, At 380,000 years after the Big Bang, the universe crossed a critical threshold. The glowing fog cleared, light streamed freely for the first time, and atoms, the fundamental building blocks of everything, were born. The stage was finally set for gravity to begin pulling these atoms together, forming the first stars and galaxies. What began as pure energy had now cooled and organized itself into the simplest elements of matter, ready to participate in the great story of cosmic evolution. When recombination finally allowed electrons to settle into orbit around nuclei, the universe became populated with the very first true atoms. But the periodic table at this stage of cosmic history was astonishingly simple. Nearly all of these first atoms were hydrogen and helium, with only the faintest sprinkling of lithium. In fact, if you imagine lining up every atom in existence shortly after recombination, about 75% of them would be hydrogen, roughly 25% would be helium, and fewer than one atom in a billion would be lithium. That was it. 3 elements, no more. Hydrogen, the simplest and most abundant atom, is just a single proton with 1 electron. Its simplicity made it not only the first atom to form but also the most enduring. Hydrogen was the raw material from which stars would later ignite, and its prevalence has defined much of the cosmic story. Even today, hydrogen remains the most abundant element in the universe, making up the majority of all baryonic matter, that is, the normal matter that forms galaxies, stars, and planets. Helium, the second most common element formed in the early universe, was the product of those intense fusion reactions that occurred within the first few minutes after the Big Bang. Each helium atom is made of 2 protons and usually 2 neutrons, with 2 electrons orbiting around them. Helium was harder to make than hydrogen, requiring multiple protons and neutrons to fuse together. But the universe's brief burst of Big Bang nucleosynthesis created a substantial amount of it. By the time recombination happened, helium atoms were forming right alongside hydrogen. And then there was lithium, the rarest of the 3. Lithium's presence in the early universe was tiny, almost negligible, but still worth mentioning. Its nuclei were formed in very small amounts during Big Bang nucleosynthesis, but conditions weren't favorable for large-scale lithium production. Later, processes inside stars and cosmic rays would add a bit more lithium to the universe, but for the most part, lithium remained a trace element, like a cosmic afterthought in the first act of creation. This striking simplicity of the early universe's chemistry is almost poetic. Out of the unimaginable violence and heat of the Big Bang, the cosmos emerged with a handful of fundamental ingredients: hydrogen, helium, and a whisper of lithium. Yet from these 3 atoms, the rest of cosmic history would unfold. Stars would be born from massive clouds of hydrogen and helium. Inside those stars, nuclear fusion would ignite, forging heavier elements step by step. In this way, the bare-bones chemistry of the early universe became the foundation for the dazzling complexity of the periodic table and, ultimately, for life itself. It's also remarkable that we can still see evidence of this primordial distribution today. When astronomers look at the most ancient stars and galaxies, they measure the proportions of hydrogen and helium and find them to be almost exactly as predicted by Big Bang nucleosynthesis. That alignment between theory and observation is one of the most compelling pieces of evidence that the Big Bang really happened. The overwhelming dominance of hydrogen and helium in the cosmos is not a coincidence. It's a direct fingerprint of the universe's fiery birth. But perhaps the most profound part of this story is what these atoms represent. Hydrogen and helium were the blank canvas on which the universe would paint its masterpiece. They were the building blocks waiting to be transformed into heavier elements through the lives and deaths of stars. Every atom of oxygen in your lungs, every carbon atom in your cells, every calcium atom in your bones, all of those had to wait billions of years to be forged from the simple hydrogen and helium born after the Big Bang. Without this initial simplicity, without the overwhelming dominance of hydrogen and helium, the universe might never have had the material or the pathways necessary to create complexity. So, in those early moments after recombination, the universe was elegant in its minimalism. Oceans of hydrogen atoms, seas of helium atoms, and tiny specks of lithium drifting through the darkening cosmos. These were the first true atoms, silent and simple, yet holding within them the potential to become everything: stars, galaxies, planets, and even us. The fact that the universe began its atomic history with only hydrogen, helium, and a trace of lithium might sound almost underwhelming at first. 3 elements out of the rich tapestry of over 100 known today. But in reality, this simplicity was not a limitation. It was the foundation of everything that would come later. These primordial atoms were like the alphabet of the cosmos. With just a few letters, an infinite number of words can be written, and with just a few atomic building blocks, the universe eventually crafted all the matter and complexity we see today. Why is this important? Because hydrogen and helium were not just the first atoms, they were the raw fuel of creation. Clouds of hydrogen and helium were pulled together by gravity to form the very first stars. Without them, no stars could have ignited, and without stars, no heavier elements would ever have been created. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these atoms exist only because the first generation of stars had hydrogen and helium to burn and fuse. In a very real sense, those earliest atoms acted as the gateway through which the universe transitioned from a simple, almost uniform state to one capable of producing extraordinary complexity. Hydrogen, being the simplest and most abundant atom, became the central character in this cosmic drama. When massive clouds of hydrogen gas collapsed under the pull of gravity, the density and pressure at the core of these clouds became so intense that nuclear fusion could ignite. That fusion turned hydrogen into helium, releasing vast amounts of energy in the process. This was the birth of the first stars, the cosmic engines that lit up the dark universe and began producing the heavier elements. Helium, though already present, also played a vital role, acting as the next step in the chain of fusion reactions that created new elements deep within stellar furnaces. But even before stars took over, the very presence of hydrogen and helium defined the large-scale structure of the cosmos. These atoms clustered under gravity, forming immense clouds that would collapse into galaxies. Without them, there would have been no material for galaxies to form at all. Imagine the universe without stars, without galaxies, without planets, just an endless void of empty space. That was the alternative, had hydrogen and helium not been created in such abundance in the early universe. The importance of these atoms also lies in their persistence. The hydrogen atoms formed nearly 14 billion years ago are still around today, still floating in interstellar space, still providing the primary ingredient for star formation. They are timeless, eternal witnesses to the universe's journey. Every time a new star is born, it is tapping into the same hydrogen reservoir that was created in the first few minutes after the Big Bang. This continuity connects us directly to the earliest chapter of cosmic history. Another layer of significance is philosophical. Hydrogen and helium remind us that the universe is not inherently complex. Complexity emerges gradually, step by step, from simple beginnings. Just as life on Earth evolved from simple organisms into an intricate web of ecosystems, the universe itself evolved from simple atoms into galaxies, stars, planets, and life. The fact that the universe started with such minimal building blocks underscores how much can be achieved from simplicity given time, energy, and the laws of physics. So, when we say that hydrogen and helium were the foundation of everything else in the universe, it's not exaggeration, it's literal truth. Without them, there would have been no stars, no chemistry, no periodic table, no Earth, no life. They were the blank page on which the universe wrote its story. And every complex atom in your body today is a testament to the fact that the cosmos didn't need to begin with everything, it just needed to begin with something. Those simple atoms were that something, the indispensable foundation for all the richness that followed. Once the universe had cooled enough for hydrogen and helium atoms to settle into existence, the next great act of cosmic evolution could finally begin. Gravity, the quiet but relentless sculptor of the cosmos, began gathering these atoms into enormous clouds. Over millions of years, these clouds grew denser and hotter until their cores reached the extreme pressures and temperatures needed to spark the first nuclear fires. With that ignition, the very first stars were born. And with their birth came the transformation of the universe itself, because stars are not just shining lights in the sky, they are atom factories, the forges where the simplest elements are turned into the diverse building blocks of matter. To appreciate this, think about hydrogen, the most common atom created after the Big Bang. Alone, hydrogen is simple, just a proton and an electron. But when enough hydrogen is compressed under gravity, the pressure and heat in the core of a star strip electrons away and force hydrogen nuclei, protons, to collide and fuse together. This process, called nuclear fusion, is the heart of a star's power. In the cores of stars, hydrogen nuclei slam into each other with such intensity that they overcome their natural repulsion and bind together, forming helium nuclei. In the process, a small fraction of their mass is converted into energy, released as light and heat, according to Einstein's famous equation, E equals mc squared. That energy is what makes a star shine. But the story doesn't end with hydrogen turning into helium. As stars age, their fusion processes evolve. In the hearts of larger stars especially, the fusion furnace grows hotter and more complex. Once most of the hydrogen in the core has been consumed, the star begins fusing helium into heavier elements like carbon and oxygen. Later still, in the lives of massive stars, fusion can progress even further, producing elements like neon, magnesium, silicon, and eventually iron. Each new round of fusion creates atoms more complex than the last, layering them like the rings of a cosmic onion deep inside the star. This is why stars are often described as alchemical workshops, tirelessly forging new elements out of the simple hydrogen and helium that were born in the Big Bang. Without stars, the universe would still be a sea of those two atoms, simple and unchanging. Stars brought chemistry into the cosmos. They introduced variety and richness into the atomic inventory of the universe, laying the groundwork for planets, for water, for rocks, for plants, and ultimately for us. It's almost humbling to consider that everything we think of as stuff in the universe, every material thing we've ever touched, comes from this stellar process. The carbon in your DNA was made inside a star. The oxygen you breathe was made inside a star. Even the calcium in your teeth and the iron in your blood were once nuclear fuel burning at millions of degrees inside a star that lived and died billions of years ago. Stars are not just beautiful ornaments of the night sky. They are the factories that made it possible for matter to become complex enough to build living beings. The role of stars in this process is also crucial to the universe's narrative of growth and change. Hydrogen and helium alone were insufficient to create planets or biology. They made up the cosmic canvas, but stars painted upon that canvas the colors of diversity by creating new elements. Each generation of stars added to the richness of the universe's chemistry. When stars died, they scattered their creations back into space, seeding the next generation of stars, and eventually, solar systems like ours. In a very real sense, stars are the link between the simplicity of the Big Bang and the complexity of life. They act as both creators and destroyers, consuming hydrogen and helium, producing heavier elements, and then releasing those elements back into the cosmos through their deaths. Without them, there would have been no way to bridge the gap between the bare-bones chemistry of the early universe and the full periodic table we see today. So when we look up at the stars, what we're really seeing are factories of creation, tirelessly working for billions of years to turn simplicity into complexity. They are the universe's original alchemists, transforming light elements into the heavy atoms that would one day become galaxies, planets, and people. Stars are the universe's way of building itself, step by step, atom by atom. Inside every star lies a secret world of unimaginable heat and pressure, a place where atoms are not just stable structures floating in space, but participants in a cosmic dance of transformation. This is the process of stellar fusion, the nuclear reactions that occur deep within a star's core. Fusion is the mechanism that allows stars to shine, but more importantly, it is the process that slowly constructs the heavier atoms needed to build planets, ecosystems, and life. Without stellar fusion, the periodic table would stall at hydrogen and helium, and the universe would be forever barren and simple. The story begins with hydrogen fusion, also called the proton-proton chain, which dominates in stars like our Sun. Here, at core temperatures of around 15 million degrees Celsius, individual protons, hydrogen nuclei, collide with such force that they can overcome their natural electric repulsion. When they smash together, one of the protons transforms into a neutron through a quantum process, and together they form deuterium, a heavy isotope of hydrogen. This deuterium nucleus can then fuse with another proton to make helium-3, and two helium-3 nuclei can fuse to form helium-4, releasing additional protons and vast amounts of energy along the way. Every step in this chain releases bursts of energy in the form of light and neutrinos, and that is what powers the star's brilliance. But hydrogen burning is only the first act. In stars more massive than the Sun, when hydrogen fuel in the core runs low, the core contracts under gravity, raising the temperature and pressure high enough for helium fusion to begin. This stage, called the triple alpha process, is where helium atoms collide and combine to form carbon. Sometimes, carbon nuclei capture an additional helium nucleus, leading to oxygen. The triple alpha process is critical because it produces two of the most essential atoms for life: carbon, the backbone of organic chemistry, and oxygen, the element that fuels metabolism and forms water. It is no exaggeration to say that life as we know it depends on this stage of stellar fusion. In even more massive stars, the story continues. Once helium is exhausted in the core, temperatures climb again, reaching hundreds of millions of degrees. At these extreme conditions, carbon nuclei themselves begin to fuse, forming neon, magnesium, and sodium. As fusion stages progress, stars move into what scientists call advanced burning phases. Oxygen fusion follows carbon burning, creating elements like silicon, sulfur, and phosphorus. These are not abstract chemical names. They are the ingredients of rocks, soils, and even the molecular machinery inside living cells. Silicon, for instance, makes up much of Earth's crust, and phosphorus is crucial for DNA and cellular energy transfer. Eventually, in the largest stars, fusion pushes to its limit with silicon burning. At core temperatures of billions of degrees, silicon nuclei fuse to create iron. Iron is the end of the line for fusion inside stars because fusing iron does not release energy, it consumes it. Up until this point, every fusion reaction inside a star has been exothermic, meaning it produces more energy than it requires, allowing the star to maintain its equilibrium. But iron is the dead end. Once a star's core is filled with iron, fusion can no longer support the star against the crushing pull of gravity. This sets the stage for dramatic events like supernova explosions. But the importance here is that by this point, the star has already forged a vast array of elements that would never have existed without the extraordinary pressures of its nuclear furnace. Think about the staggering implication of this. The carbon that forms the backbone of your DNA, the oxygen in every breath you take, the calcium that strengthens your bones, and the iron carrying oxygen in your blood were all manufactured in stellar cores through these fusion processes. The very atoms that keep you alive were once forged in the heart of a star. Fusion is not just an abstract physical process. It is the reason the universe has any structure, chemistry, or biology at all. What makes stellar fusion even more remarkable is its efficiency and elegance. From the simplest particle interactions, guided only by the fundamental forces of physics, nature builds up layer after layer of atomic complexity. No outside intervention is needed, no designer is required, just the basic rules of nuclear physics operating over billions of years. Hydrogen and helium become carbon and oxygen, which in turn become neon, silicon, and iron. The universe, through stars, builds its own ingredients for life. So when you gaze at the night sky, you're not simply looking at distant points of light, you're looking at furnaces that are actively shaping the future of the cosmos. Each star is a nuclear reactor on a scale beyond imagination, slowly but surely constructing the atoms that will one day make new planets, new systems, and possibly new forms of life. Stellar fusion is the quiet but relentless architect of the universe's diversity, the process that took the cosmos from simplicity to the breathtaking complexity we know today. When a massive star nears the end of its life, a dramatic and violent transformation takes place, one so powerful that it reshapes the cosmos itself. This is the supernova, one of the most cataclysmic events the universe can produce. For most of its life, a massive star is able to balance two opposing forces: the inward pull of gravity trying to collapse it and the outward pressure of energy released by nuclear fusion in its core. This balance, known as hydrostatic equilibrium, keeps the star stable for millions of years. But when the star finally begins to fuse silicon into iron, it unknowingly seals its fate. Iron, as remarkable as it is, represents a dead end for nuclear fusion. Unlike lighter elements, which release energy when fused, iron consumes energy in the process. Once the core of a star becomes predominantly iron, no further energy can be generated to counteract gravity. At this moment, the delicate balance collapses. Gravity wins. The iron core implodes in a fraction of a second, compressing into an incredibly dense state. Temperatures soar to billions of degrees, and the inner layers of the star collapse inward at astonishing speeds. But just as suddenly, the implosion rebounds. The outer layers of the star crash into the rigid, incompressible core and are blasted outward in a titanic explosion, a supernova. This explosion releases an almost incomprehensible amount of energy. For a brief moment, a single star can outshine an entire galaxy containing hundreds of billions of stars. To put it into perspective, the energy released in a supernova can be greater than the total energy the Sun will emit in its entire 10 billion-year lifetime. The brilliance of a supernova is so intense that ancient astronomers recorded these sudden guest stars in the sky, sometimes visible even in daylight. But beyond their spectacular light show, supernovae are essential for a far deeper reason. They are the cosmic events that scatter heavy elements across the universe. During the explosion, the immense energy and pressure trigger nuclear reactions far beyond what even the largest stars could accomplish in their cores. This process, known as nucleosynthesis, produces the heaviest elements in the periodic table: gold, uranium, platinum, and other rare elements. Those that fusion inside stars cannot create, are forged in the fleeting chaos of the explosion. These elements are then hurled into interstellar space, enriching the cosmic environment with new atomic possibilities. Imagine the universe before the first supernovae. It was filled with hydrogen, helium, and the lighter products of stellar fusion like carbon, oxygen, and iron. Useful, yes, but incomplete. Without supernovae, there would be no copper to wire our technology, no iodine for our thyroids, no golden jewelry, no uranium to power nuclear plants. The very existence of these heavier atoms in the cosmos is owed to the death throes of massive stars. Every time we use or encounter such elements, we are handling material created in a cosmic explosion billions of years ago. The debris from these stellar deaths does not simply drift away aimlessly. Instead, it becomes the seed material for the next generation of stars and planets. Interstellar clouds, enriched by the remnants of supernovae, collapse under gravity to form new systems, carrying within them the heavy atoms that make rocky planets and living beings possible. Our own solar system was born from such a cloud, already infused with the products of countless supernovae that had occurred before it. That is why Earth is rich in diverse elements and why life could arise here in the first place. In this way, supernovae act as both endings and beginnings. They mark the violent deaths of massive stars, but they also lay the groundwork for new stars, new planets, and eventually new forms of life. They are the mechanism by which the universe recycles itself, ensuring that each generation of cosmic objects is richer and more complex than the last. The very atoms in your bones, the iron in your blood, the calcium in your teeth, these were once part of the core of a star that died in a spectacular supernova billions of years ago. You carry within you the ashes of stars, scattered across the universe by explosions so powerful that they still echo in the cosmos today. When you think about supernovae in this light, they become more than just astronomical curiosities. They are the heartbeat of cosmic evolution, the punctuation marks in the universe's story of creation. Without them, the cosmos would be a stagnant place, locked forever in the simplicity of hydrogen and helium. With them, the universe becomes dynamic, ever-changing, and capable of giving rise to the extraordinary diversity of matter and life that we see today. When we look at the periodic table of elements, it's easy to see it as just a classroom chart, rows and columns of symbols and numbers neatly arranged on a wall. But the truth is far more profound. That table is not simply a catalogue of chemistry, it is the autobiography of the universe written in atomic form. Every single square on that chart, from the humble hydrogen at the very top to the exotic heavy elements at the far end, tells a story of cosmic processes that unfolded over billions of years. The periodic table is essentially the universe's family tree, showing us where the very atoms that make up our world originated. At the very beginning, the table was almost empty. The Big Bang supplied hydrogen, helium, and a whisper of lithium. That was it. Those three elements filled the universe for hundreds of millions of years, drifting in vast clouds, waiting for the next stage of cosmic creation. On the periodic table, that's only the very first row and a tiny corner of the second. If the universe had stopped there, life would never have been possible. But then stars were born, and the chart began to fill. In the blazing cores of stars, fusion began to build the lighter elements up the table. Helium fused into carbon, carbon into oxygen, oxygen into neon and magnesium, building step by step through silicon and eventually to iron. These middleweight elements, spanning from carbon to iron, represent the products of stellar fusion, the ordinary, steady burning of stars that light the skies. Stars could not go any further on their own, because iron, as we've seen, cannot release energy through fusion. So the periodic table, at this stage, still had great gaps waiting to be filled. That's where supernovae and other cosmic phenomena stepped in. When massive stars exploded, they not only scattered their iron cores and carbon-rich shells into space, but they also triggered nuclear reactions of staggering violence. In those fleeting moments of chaos, the heavier elements were forged: the gold, the silver, the uranium, the lead. Processes known as rapid neutron capture, or the R process, flooded nuclei with neutrons, allowing them to climb the table into entirely new territories of complexity. In fact, every heavy element beyond iron owes its existence to such cataclysmic events. Without these explosions, half the periodic table would never have come into being. But supernovae weren't the only contributors. In more recent years, scientists have discovered that neutron-star collisions, when two ultradense remnants of dead stars crash together, are also factories of heavy elements. These cosmic collisions are so extreme that they eject vast quantities of precious metals like gold and platinum into the galaxy. This means that the ring on your finger or the circuitry in your phone might have been born not just in a supernova, but in the titanic merger of neutron stars billions of years ago. The periodic table, therefore, is not the product of one single process, but of a symphony of cosmic events, each one adding its own notes to the grand composition of matter. As we trace our way through the table, we can see this cosmic layering unfold. The first two rows, hydrogen, helium, lithium, are the legacy of the Big Bang. From carbon through iron, we see the handiwork of stellar fusion. Beyond iron, we encounter the fingerprints of supernovae, neutron star mergers, and exotic astrophysical processes. Even the rarest and most unstable elements, which decay rapidly on Earth, remind us that the universe is always experimenting, always creating and recycling in ways we are still striving to understand. So when you study the periodic table, you are not just memorizing symbols and numbers. You are looking at the condensed history of cosmic evolution. It is the record of how energy transformed into matter, how simple atoms became complex, and how the universe's vast machinery created the diversity of elements necessary for planets, oceans, mountains, forests, and living beings. Every single square is a chapter in that story. Oxygen means breath. Carbon means life. Iron means blood. Calcium means bones. Gold and platinum mean cosmic violence on a scale beyond imagination. The periodic table is, in essence, a cosmic map. It reminds us that the matter we work with every day, whether in science labs or in the kitchen, is not ordinary at all. It is the direct inheritance of stellar furnaces and cosmic explosions. It shows us that there is no separation between the chemistry of life and the physics of the universe. The chalk on a blackboard, the silicon in a computer chip, the potassium in a banana, the zinc in our enzymes, all of it was made possible by processes that took place billions of years before Earth was even formed. So the next time you glance at that familiar chart, imagine it glowing with the light of stars, each element labeled not just with its chemical symbol, but with its cosmic birthplace: hydrogen from the Big Bang, carbon from stellar fusion, gold from a supernova, uranium from a neutron star merger. The periodic table isn't just a tool for chemists, it's a monument to the universe's creativity, showing us in one glance how nothing transformed into everything. Once the universe had a diverse collection of atoms, hydrogen, helium, and eventually the heavier elements forged in stars and supernovae, another force took center stage in shaping the cosmos: gravity. Gravity is the invisible sculptor of the universe, the quiet but relentless force that takes scattered atoms and pulls them together into grand structures. Without it, atoms would remain as lonely wanderers drifting endlessly through the void. With it, those same atoms gather into clouds, ignite as stars, cluster as galaxies, and eventually form planets, oceans, and even living beings. To appreciate the role of gravity, we have to step back and imagine the young universe after recombination, when the first atoms finally came into existence. The cosmos was filled with a nearly uniform sea of hydrogen and helium, spread thinly across vast distances. But it wasn't perfectly uniform. Tiny fluctuations in density, seeded by quantum fluctuations from the earliest moments of the Big Bang, created slightly denser patches of matter. Though these variations were almost unimaginably small, gravity amplified them over time. Regions with just a little more matter pulled in even more, becoming denser still, while less dense regions grew emptier. This runaway process led to the clumping of matter, the first step toward the cosmic structures we see today. As clouds of hydrogen and helium gas grew larger under gravity's pull, they began to contract. When atoms crowd together, their motion heats the cloud, and at a certain point, the core becomes hot and dense enough for nuclear fusion to ignite. This is how the first stars were born, immense gas clouds collapsing under their own weight, heating up until they burst into nuclear fire. These stars lit up the darkness of the early universe, producing light where before there had been only shadows. They also began the long process of forging heavier elements, which would later enrich the universe even further. Gravity did not stop with stars. On larger scales, it pulled stars together into clusters and galaxies. Billions of stars formed in each galaxy, orbiting in intricate patterns around central supermassive black holes. Over billions of years, galaxies collided and merged under gravity's attraction, shaping the cosmic web we see today. The Milky Way, our home galaxy, is the result of countless mergers and gravitational interactions that slowly wove together its spiral structure. But perhaps the most intimate role of gravity was in the creation of planets and, eventually, worlds like Earth. When stars form, not all of the gas and dust falls into the star itself. Some of it remains in orbit, flattened into a spinning disk. Within this protoplanetary disk, gravity began gathering dust grains into clumps, clumps into boulders, and boulders into planetesimals, the building blocks of planets. Over millions of years, collisions and accretion under gravity's guiding hand sculpted full-fledged planets. Rocky planets like Earth, Mars, and Venus formed close to their stars, while gas giants like Jupiter and Saturn grew massive in the outer regions. Even once planets were born, gravity continued its work. It bound atmospheres to planets, kept moons in orbit, and orchestrated the complex ballet of solar systems. Without gravity, Earth would have no atmosphere, no oceans, no stable orbit around the sun. Life as we know it would be impossible. Gravity is not just a cosmic builder, it is also a preserver, maintaining the delicate balance that allows stars to burn steadily and planets to support ecosystems. On the grandest scale, gravity still shapes the destiny of the universe itself. Galaxies are held together by their mutual gravitational attraction, and galaxy clusters are bound by the same force. The large-scale structure of the universe, the cosmic web of filaments and voids we now observe with powerful telescopes, is nothing less than the footprint of gravity acting on atoms across billions of years. Even dark matter, the mysterious invisible substance that outweighs normal matter 5 to 1, reveals itself only through gravity. Its unseen mass provides the extra pull needed to explain why galaxies hold together the way they do. So when we think about gravity's role in the story of atoms, it's clear that this force is not just another detail, it is the architect of complexity. Atoms on their own are remarkable, but scattered randomly through space, they are inert and purposeless. Gravity gives them direction. It gathers them, compresses them, ignites them, and sculpts them into stars and planets. It provides the conditions for fusion, for chemistry, for biology. Without gravity, there would be no galaxies to gaze upon, no Earth beneath our feet, and no you or me to ask the question of how atoms came from nothing. The atoms of hydrogen and helium that once floated freely after the Big Bang were only the beginning. It was gravity that brought them together, ignited them, and recycled them through generations of stars. It was gravity that gathered star-forged elements into the rocky world we call home. It was gravity that made sure the story of atoms did not end with scattering but continued into structure, complexity, and ultimately, life. When we take a step back from the vast cosmic scales of galaxies and stars and look inward, toward ourselves, we begin to realize that the story of atoms is not just about the distant universe, it is about us. Every cell in your body, every breath you take, every beat of your heart is possible because of atoms. And those atoms, remarkably, were not formed on Earth, nor were they born within our solar system. They came from ancient stars that lived and died billions of years before our planet even existed. The connection is direct, intimate, and astonishing. You are literally made of stardust. Consider carbon, one of the most essential atoms in your body. Carbon is the backbone of life. It forms the framework of DNA, proteins, sugars, and countless other molecules that make biology possible. Without carbon, chemistry could never have leapt into the complexity required for living systems. And yet, carbon did not appear in the Big Bang. The early universe had no carbon at all. Carbon was first forged deep inside stars, where helium nuclei fused together in a delicate chain of reactions known as the triple alpha process. Billions of years ago, a massive star created the carbon that eventually became part of your body. Now think about oxygen. Every time you inhale, oxygen rushes into your lungs, fueling the chemical reactions that power your cells. Oxygen makes up about 65% of the human body by mass, more than any other element. And like carbon, oxygen was not present in the earliest universe. It too was forged in the cores of stars, created when helium and carbon fused under immense heat and pressure. Later, when those stars died in supernovae, they scattered oxygen into space, where it mixed into the clouds that would one day form our solar system. Even the iron in your blood, the element that allows red blood cells to carry oxygen throughout your body, has a dramatic cosmic origin. Iron is unique because it represents the limit of what normal stellar fusion can produce. Once iron forms in a massive star, fusion no longer releases energy, and the star collapses, leading to a violent supernova explosion. That explosion hurled iron into space, where it eventually became part of Earth's crust and part of your bloodstream. Every time your heart beats, pumping iron-rich blood through your veins, you are living proof of a supernova that occurred billions of years ago. And let's not forget calcium, the element in your bones and teeth. Without calcium, your skeletal structure could not exist, and life as you know it would be impossible. Calcium too was forged in the final stages of stellar fusion, as massive stars churned their elements in fiery cores. Magnesium in your cells, potassium in your nerves, phosphorus in your DNA, and trace elements like zinc and copper, all of them were born in stars and scattered into the cosmos by stellar winds and explosions. This realization is staggering. The very atoms that make up your body traveled an unimaginably long and ancient journey. They were born in the heart of stars, released into space through violent deaths, carried across interstellar clouds, swept into the birth of our solar system, incorporated into the Earth, and eventually became part of you. When you look in a mirror, you are not just seeing a human being. You are seeing a collection of atoms that have been recycled and repurposed for billions of years. You are, in the most literal sense, a piece of the universe that has become aware of itself. This connection to the cosmos dissolves the illusion that we are separate from the universe around us. The carbon in your cells is the same carbon found in distant galaxies. The oxygen in your breath is the same oxygen floating in nebulae. The iron in your blood is the same iron scattered throughout the remnants of ancient stars. We are not observers standing apart from the universe. We are participants, constructed from its very fabric. And when we think about it even further, this truth carries profound implications. It means that life on Earth is not an accident isolated to one small planet, but rather a continuation of cosmic processes that began with the Big Bang. It means that the chemistry of life is directly tied to the physics of stars, and that our story is inseparable from the story of the universe. Every heartbeat is part of a chain reaction that stretches back to the birth of atoms themselves. So, the next time you feel small when gazing at the night sky, remember this: the stars are not just distant points of light. They are your ancestors. The atoms that compose you were once inside those stars, fused in their fiery cores, and released into space long before Earth was born. To say that we are connected to the universe is not poetry, it is scientific truth. You are not just in the universe. You are of the universe. You are made of the same stuff as galaxies, nebulae, and supernovae. The phrase "we are stardust" has been repeated so often that it risks sounding like a metaphor, a piece of poetic imagination meant to inspire wonder. But the breathtaking fact is that it is not merely a metaphor at all, it is literal, scientific truth. Every atom heavier than hydrogen and helium, every essential ingredient for life, every stone, tree, river, and mountain on Earth, and every cell in your body originated from processes that took place in the hearts of stars. The cosmos is not something out there, distant and detached from us. It is within us. It is us. To fully grasp the weight of this idea, let's take a walk through its meaning. Hydrogen and helium, the simplest atoms, formed in the immediate aftermath of the Big Bang. They filled the young universe, but by themselves, they could not make worlds or life. Stars emerged as engines of transformation, igniting fusion in their cores. From hydrogen, they built helium. From helium, they forged carbon and oxygen. And from those, They work their way up the ladder of elements, producing nitrogen, magnesium, silicon, sulfur, and iron. These elements are the scaffolding of complexity, the essential palette from which planets and living organisms are painted. But those elements could not remain locked away inside stars. For them to become part of planets and people, stars had to die. Some stars shed their outer layers gently, enriching space with carbon and nitrogen. More massive ones exploded in cataclysmic supernovae, hurling oxygen, silicon, and iron into the cosmos with violent force. These events seeded the interstellar medium, the vast clouds of gas and dust that drift between stars, with the raw materials of future solar systems. Over billions of years, gravity gathered these enriched clouds into new stars and planets. And within that cycle, on at least one world orbiting an average star in a spiral galaxy, some of those atoms assembled into molecules that became alive. That is the context in which you and I exist. The oxygen in our lungs, the calcium in our bones, the carbon in our DNA, and the iron in our blood all once burned inside stars and were carried across the galaxy before being woven into our bodies. When you breathe, you are breathing the exhalations of ancient stars. When you stand on the Earth, you are standing on a planet built from stardust. This realization blurs the line between science and poetry. The poetry lies in the imagery, imagining that the golden autumn leaves, the oceans rolling under the sun, or the warmth of a human hand all trace back to the violent deaths of stars billions of years ago. But the science makes it even more profound. This isn't an allegory, it's astrophysics. Carl Sagan's famous line, "We are made of star stuff," wasn't intended to be a slogan. It was a precise observation about nuclear fusion, stellar death, and cosmic recycling. The phrase also reshapes how we view ourselves in the grand scheme of existence. Human culture often separates us from nature, and certainly from the wider cosmos, as though we are spectators looking outward into a universe that is fundamentally alien. But the truth is the opposite. There is no separation. The atoms of our bodies and the atoms of distant galaxies are siblings, born of the same processes, connected by the same physics. When we look up at the night sky, we are not gazing at something other. We are gazing into our own origins, into the cosmic family to which we belong. The "we are stardust" idea also has philosophical weight. It humbles us by showing that we are tiny participants in an unimaginably vast cosmos, yet it elevates us by revealing that the universe has grown so complex through its natural processes that it has produced beings who can reflect upon their own origins. Out of stardust came not only matter, but also minds, capable of asking questions, writing poetry, building telescopes, and seeking meaning. In that sense, the atoms of the cosmos have become self-aware in us. We are the universe contemplating itself. It is also worth noting that this truth unites us with everything else we see. The trees outside your window, the rocks under your feet, the oceans that stretch across the earth, all are stardust. The dog sitting beside you, the bird soaring overhead, and the stranger walking on the other side of the world all share the same elemental heritage. We are all variations of the same cosmic story, written in different forms. The entire biosphere is a single unfolding of stardust organized into life. To say we are stardust is therefore to acknowledge a kinship that transcends species, planet, or even galaxy. It reminds us that we are not accidents adrift in emptiness, but rather the latest expression of a universe that has been creating, collapsing, and renewing itself for 13.8 billion years. Our atoms have traveled through time and space, survived stellar furnaces and explosions, and eventually come together here, in this moment, to form us. So, the next time you see the stars twinkling in the night sky, pause to reflect on the fact that you are not merely looking at them, you are connected to them. You are their continuation. You are their product. You are their descendant. We are stardust is not only a statement of physics, but a reminder of belonging, a cosmic truth that transforms how we see both the universe and ourselves. When we return to the mystery of nothing, it becomes clear that this single word has carried far more weight than most people realize. To the human mind, nothing seems like the simplest concept in the world, an absence, a void, a blankness without shape, energy, or existence. But when science asks the question, what is nothing? The answer takes us down a rabbit hole into some of the strangest and most counterintuitive discoveries of modern physics. And this is where our story about the origins of atoms takes its most astonishing turn. For much of human history, nothing meant emptiness, an infinite darkness with no matter and no activity. But physics has shown that even the deepest emptiness is not truly empty. Even when you strip away all matter, all light, and all heat, there still remains something called the quantum vacuum. This vacuum isn't a simple blankness. It is a field, a stage upon which the drama of existence unfolds. Invisible to our senses, it is teeming with possibility, and it never sits still. According to quantum mechanics, every point in space is filled with fluctuating fields that can never reach absolute stillness. They vibrate ever so slightly, a jitter that can never be turned off. This jitter is not noise, it is fundamental. Because of it, tiny pairs of particles and antiparticles pop into existence, exist for the briefest flicker of time, and then vanish again. These are called virtual particles, and though they cannot be observed directly in the same way as stable matter, their presence is undeniable. We have seen their fingerprints in experiments, in subtle shifts of energy, and in phenomena. Like the Casimir effect, where the invisible pressure of quantum fluctuations can push two metal plates together. The very fact that virtual particles can appear spontaneously suggests something profound: nothing has the power to create. This idea is both unsettling and liberating. It means that the leap from absence to presence, from emptiness to something, is not impossible. It is natural, permitted, even inevitable, when viewed through the lens of quantum physics. Now imagine scaling up this principle. If tiny particles can arise from the vacuum, what about entire bursts of energy? What about space itself? Some cosmologists propose that the Big Bang itself, the moment from which our universe sprang, may have been the result of a quantum fluctuation, an extraordinary event where the underlying vacuum released a pocket of energy that expanded into everything we see today. In this picture, the universe did not come from a void in the classical sense, but from a fertile quantum background that has always had the capacity to give rise to reality. This explanation does not end the mystery, it deepens it. Because if nothing is a quantum vacuum, then what gives rise to the vacuum? If our universe emerged from a fluctuation, then what was it fluctuating within? Was there a larger reality, a multiverse, an infinite quantum sea bubbling with universes? Or is our concept of before the Big Bang meaningless, since time itself only began with that event? These are questions physics has not yet answered, and perhaps never fully can. And yet, even with these uncertainties, one fact remains. The atoms of our bodies, the matter that fills the galaxies, the stars that shine in the night sky, all ultimately owe their existence to the fact that nothing in physics is not truly nothing. The restless, creative vacuum has the power to give birth to particles, and with them, the story of matter begins. Without that, there would have been no quarks, no protons, no hydrogen, no stars, no carbon, no Earth, no us. So when we say atoms came from nothing, we must say it carefully. They came not from a perfect void, but from a fertile field of fluctuations, an invisible fabric humming with the possibility of creation. This reframes our understanding of reality itself. What we thought of as emptiness is actually the most fundamental something of all, the source of everything. The idea of quantum fluctuations is one of the most mind-bending concepts in physics, and yet it may hold the key to explaining how the universe itself began. When we speak about fluctuations, we're describing the restless jitter of the quantum vacuum, a seething foam of energy that never quite rests, even when it appears to us as empty space. This jitter is so fundamental that it cannot be turned off. It is woven into the laws of nature. At the tiniest scales of reality, uncertainty rules. Energy can rise and fall spontaneously, particles can appear and vanish, and fluctuations in fields ripple unpredictably. Normally, these fluctuations are microscopic, fleeting, and insignificant on cosmic scales. They wink in and out of existence in less than a trillionth of a second, leaving almost no trace. But under the right conditions, something extraordinary can happen. One of these fluctuations can grow, triggering a runaway process that births something far greater than itself. This is one of the leading ideas for how our universe began. Imagine, for a moment, the early quantum vacuum as a vast ocean of possibility. On its surface, ripples are constantly forming and disappearing. Most ripples fade instantly, but what if one ripple didn't collapse? What if instead it inflated, expanding at a staggering rate, fueled by the very energy of the vacuum itself? That runaway inflation could create an entire universe. And according to many cosmologists, that is precisely what may have happened nearly 13.8 billion years ago. A quantum fluctuation sparked the Big Bang. Now, it's important to clarify that when we say fluctuation, we're not talking about a fluctuation within pre-existing space and time. The Big Bang was not an event within a larger void, it was the birth of space and time itself. A quantum fluctuation may have created not just the matter and energy we see today, but the very fabric of reality. The expanding space in which galaxies, stars, and eventually we ourselves came to exist. This is one of the remarkable implications of quantum theory. Because energy can fluctuate spontaneously, and because Einstein's relativity allows energy to be converted into matter, the seeds of everything we know could have been planted by the smallest possible flicker of energy. From that flicker came expansion. From expansion came cooling. From cooling came particles. From particles came atoms. And from atoms, after billions of years of cosmic evolution, came life. Evidence for this idea comes from the detailed structure of the universe itself. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see tiny variations in temperature and density. These variations are thought to be the imprints of quantum fluctuations stretched to cosmic scales during the early inflationary period. In other words, the fingerprints of the quantum vacuum are still etched into the sky, visible in the very first light of the cosmos. Without those fluctuations, the universe would be perfectly smooth, with no galaxies, no stars, and no planets. Paradoxically, the imperfection of quantum fluctuations is what made structure, and ultimately life, possible. This transforms our view of the universe. The vast galaxies we see in telescopes, the stars that light our nights, the atoms in our bodies, all of it may trace its origin to the smallest imaginable flicker in an invisible vacuum. It suggests that creation is not a singular miracle but an expression of the fundamental rules of physics. Randomness, uncertainty, and fluctuation are not nuisances, they are the engine of existence. But of course, as with so much in cosmology, mysteries remain. If our universe arose from a quantum fluctuation, does that mean other universes are also bubbling into being in the quantum vacuum? Could our universe be just one of countless others, each born from its own fluctuation? If so, then the cosmos is not a singular object but an infinite multiverse, a frothing sea of universes, each with its own laws and possibilities. Whether or not this is true, what we know with confidence is that fluctuations, those tiny bursts of randomness at the quantum level, are not trivial. They may be the reason anything exists at all. They may be the bridge between nothingness and something, the spark that set reality into motion. And if that is the case, then everything we see, the stars above us, the earth beneath us, the people we love, and even our own thoughts, is, in some sense, the echo of a quantum fluctuation that took place nearly 14 billion years ago. Even with all the astonishing progress science has made in tracing the origin of atoms back to the very beginning, there remains a vast frontier of unanswered questions. In fact, some of the most profound mysteries of existence are not about what we already know, but about what still escapes our understanding. These mysteries are not minor details, they strike at the very foundation of cosmology, physics, and philosophy, leaving us humbled by how much is left to discover. One of the most glaring unknowns is dark matter. When astronomers study galaxies and the way they rotate, they notice something strange. The stars move as if they are being held together by far more mass than we can see. If galaxies only contained the visible matter, the stars, gas, and dust, we would expect them to fly apart. But they don't. Something invisible is providing the gravitational glue. That something is called dark matter. We call it dark because it doesn't emit, reflect, or absorb light. It is utterly invisible. We can't see it directly, and yet we know it's there because of its gravitational influence. Shockingly, dark matter makes up about 27% of the universe, while ordinary matter, the atoms that form planets, people, and everything familiar, accounts for less than 5%. That means the atoms we've spent so long tracing are only a tiny fraction of what reality is made of. The rest lies in the unseen. But dark matter is only half the puzzle. The other half is even stranger: dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down, as they had expected. Instead, it's speeding up. Something is driving galaxies farther and farther apart, accelerating the growth of space itself. That mysterious force is called dark energy, and it makes up nearly 70% of the universe. To put it differently, almost everything in existence is dark, either dark matter, which pulls galaxies together, or dark energy, which pushes them apart. The atoms we understand so well are just a tiny, glowing tip of a vast cosmic iceberg. And then there is the deepest mystery of all: what happened before the Big Bang? Our current theories are remarkably good at describing the evolution of the universe from a fraction of a second after its birth. We can model inflation, particle formation, nucleosynthesis, recombination, and the rise of structure. But what about the instant before it all began? Was there a before at all? If time itself came into being with the Big Bang, then perhaps asking what happened before is meaningless, like asking what lies north of the North Pole. But human curiosity doesn't rest so easily. Many theories attempt to address this question. Some suggest the universe is cyclical, eternally expanding and contracting in an infinite series of bangs and crunches. Others propose that our universe is just one bubble in a vast multiverse, constantly spawning new universes through quantum fluctuations. Still others look to string theory, higher dimensions, or exotic ideas that stretch the imagination. Yet despite all these theories, we simply don't know. The beginning remains cloaked in mystery, and perhaps it always will. But that's not a weakness of science, it's its strength. Admitting what we don't know is the first step toward discovery. Each mystery, dark matter, dark energy, the origin of time, reminds us that our current understanding, as magnificent as it is only a beginning. There are truths about the cosmos that no telescope has yet seen, no particle accelerator has yet revealed, and no equation has yet captured. And perhaps that is the most humbling and inspiring thought of all: the universe is not a solved puzzle. It is a living mystery, ever deeper the closer we look. Every atom in our bodies may have come from stars, but the story of atoms is not finished. It continues to unfold with every new discovery, challenging us to expand our minds and reimagine our place in the cosmos. And so we come to the end of this journey, one that began with the smallest, most fragile of questions. How could atoms, those invisible building blocks of reality, come from nothing? Along the way we've traveled across billions of years of cosmic history, from the incomprehensible moment of the Big Bang to the formation of quarks, protons, and nuclei, from the blinding plasma of the infant universe to the quiet cooling that allowed the first atoms to form. We've followed hydrogen and helium as they gathered in clouds, ignited in stars, and fused into heavier elements. We've watched massive stars collapse and explode, scattering their newly forged elements across the galaxy, seeding the raw material for worlds and life. And we've recognized that the very atoms that make up our bodies were forged in ancient furnaces, carried on the winds of exploding stars, and gathered by the pull of gravity into a planet orbiting a star we now call the Sun. From the perspective of physics, this story is breathtaking not because it is mythic or miraculous, but because it is natural. From what we once thought of as nothing, a quantum vacuum restless with possibility, came fluctuations that may have ignited the birth of the cosmos. Those fluctuations stretched and expanded, becoming the great canvas of space-time itself. Out of pure energy, matter emerged. Out of matter, atoms formed. Out of atoms, stars lit up the darkness. Out of stars, heavy elements were born. Out of those elements, planets condensed. And on one small blue planet, chemistry took a further leap. Atoms organized themselves into molecules, molecules into cells, and cells into consciousness capable of asking the very question we've explored tonight. What began as nothing is now everything. Galaxies, oceans, forests, mountains, animals, people, and thoughts. Every glance at the night sky is a reminder of this lineage. Every breath we take carries oxygen once forged in stellar cores. Every beat of our hearts is powered by chemical reactions fueled by carbon, nitrogen, and iron, atoms born in cosmic furnaces long before Earth existed. We are not separate from the universe. We are its continuation, its unfolding, its self-awareness. To think that the human story is bound so deeply to the story of the cosmos is at once humbling and exhilarating. It means that when we look inward, at our own bodies and minds, we are seeing the echo of cosmic processes billions of years in the making. And when we look outward, into the vastness of space, we are not gazing into something foreign, but into our own origins. Perhaps the most profound truth we can take away is that existence itself is extraordinary. The fact that there is something rather than nothing, that atoms could emerge from fluctuations in a restless vacuum, that stars could fuse those atoms into the elements of life, and that consciousness could arise to ponder it all, this is not just a scientific narrative. It is a source of awe, a reminder that we live in a universe more wondrous than any story we could invent. And so, the next time you look up at the night sky, remember, the atoms in your body were born in stars. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in cosmic fire and scattered across the heavens. From nothing, through physics, stars, and time, the universe became capable of asking questions about itself. We are that capability, we are that curiosity, we are that stardust come alive. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.